Hi, and welcome again to Stranger Than Fiction. I mentioned in an earlier video that one of the first clues we had that something was missing in our understanding of physics was blackbody radiation. In order to understand the light spectrum that a blackbody, like a star, gives off, scientists had to do something they'd never done before. They had to imagine that energy comes in tiny packets called quanta, and not in any smaller amounts. When they did that, it was the first step toward a whole new branch of physics we now call quantum mechanics. The idea that energy can only come in tiny packets is kind of like the idea that matter comes in tiny amounts which we know are atoms. You can think of a quantum as being like an atom of energy, and just as you can't have a piece of copper smaller than one atom, you can't have a piece of energy smaller than a quantum. Now today I want to talk about the equation that first used quanta to explain the light spectrum that a blackbody gives off. I talked a lot about blackbody radiation in that earlier video. If you haven't seen it, I hope you'll give it a look. Unlike this video, it doesn't have very much math in it, so it's a good introduction. But right now what I want to do is show you the math behind how we got that first important equation. I'd love it if some of you watching this video someday make discoveries of your own, and in order to do good science, it's important to understand how scientists use math. So, I mentioned in the earlier video that Max Planck developed this equation, called the Planck equation, to explain blackbody radiation, and now I want to explain how he came up with it. To start with, remember that the 19th century was the time of the Industrial Revolution. We invented the train and the automobile. We learned how to dig bigger and better and deeper coal mines, and mills and factories popped up all over the world. All of that was possible because of the steam engine. So people really wanted to know more about how engines and heat work. And three people who worked on that were Josiah Gibbs, James Clerk Maxwell, and Ludwig Boltzmann. The three of them developed equations to describe the energies that molecules could have, because that's important for steam engines. Here's one of their formulas, called the Boltzmann equation. Now what this says is that the probability that a molecule has the energy E is proportional to this. The number k is a constant called Boltzmann's constant, which is named after Ludwig Boltzmann. So what does the equation tell us? Well, suppose E, the energy, is really high. In that case, this will be a large number, so the fraction will be tiny. In other words, there's a small probability that the energy will be really high. On the other hand, if the energy is small, then this term will also be small, and so the fraction will be a high number. So the smaller E is, the higher the probability is. Or in other words, it's more likely that molecules will have a small energy instead of a high one. Now we want to know how many molecules will have a certain energy. So let's change this equation a little. Here's where Planck's insight came in. He said, let's imagine that the black body is made of particles that can only have certain energies. So they can have energy 1, energy 2, energy 3, and so on, but they can't have an energy in between those. That was Planck's big idea, the idea that energy only comes in little units, which he called quanta. So the idea is that if a particle has, say, energy E1, it can emit light with an energy of E1. So with that in mind, our equation changes to this. This says that nx, that's the number of particles that have an energy Ex, nx is equal to this. Now Planck suggested that the energy of a light wave is going to depend on the frequency. So E is equal to a constant times the frequency. We use this symbol, the Greek letter nu, for frequency, and the constant h is called Planck's constant. So the energy of a particle at level x is x times h nu. Now today we know that some of the assumptions Planck made weren't quite right, but he was right that the energy comes in quanta, and that's what makes it an important idea. So the overall number of particles, n, is going to be equal to the number with the lowest energy, n0, plus the number in level 1, n1, and the number in level 2, and 3, and 4, and so on. If we put the formula we just got for nx into that equation, here's what we'll get. The only difference between each term is the value of x. Now let's look at the right side more closely. In the first term, we have e raised to the 0 power. Now anything to the 0 power is equal to 1, so the first term is just n0 times 1. Now look at the other terms. They each start with n0 and then an exponential term. But look, this exponential is equal to the first one squared. And this one is equal to the first one to the third power, and so on. Each term has the same exponential, but to a power 1 higher than in the term before. So, if I call that exponential term z, I'll get this. And now if we factor out n0 from each term, the right side is just n0 times 1 plus z squared plus z cubed, and so on. Now the part in parentheses goes on forever. It has an infinite number of terms. But we can make it simpler because it turns out the bit in parentheses is just equal to 1 over 1 minus z. So now if I plug my exponential back in for z, I get this. So that's an equation for the overall number of particles. Now we might also want to know what the overall energy is. Well, the energy, E, is going to be what we get when we add the energies of all the particles. So there's a number n1 of particles with energy E1. There are n2 particles with energy E2, n3 with energy E3, and so on. So overall, the energy is this. n0 times the energy E0 plus n1 times E1 and n2 times E2, and so on. Well, we know that each energy is a multiple of h times nu, so we can put that in the equation wherever we see an E, which gives us this. But look, the lowest possible energy a particle can have is 0, so E0, which is the lowest energy, must be equal to 0. That means the first term drops out. And we know what each of these n's is equal to. We figured that out earlier. So we'll put our equation for nx wherever we see an n, and that will give us this result. Now each of the terms has an n0 and an h nu in it. So let's factor those out. And now you can see that there's a pattern. Each term has an exponential in it. In the first term, it's just plain. In the next, it's squared. In the one after that, it's cubed, and so on. That's very similar to what we saw earlier. Also, starting here, there's another factor. It's 2 in the second term, 3 in the third, then 4, and so on. So if I call the exponential z, like we did before, the term in parentheses is this. 1 plus 2z plus 3z squared, and so on. The part in parentheses has an infinite number of terms, but just like before, it turns out to be equal to something simpler. It's equal to 1 over 1 minus z, all squared. So if we put that in the parentheses, we get this. And now, if we put the exponential back instead of z, we get this result. And now we're almost done. Here are the two equations we figured out so far, one for n and one for e. If we rearrange the first one to solve for n0, we get this. Now we can pop that in for n0 in our equation for energy. If we do, here's what we'll get. Now let's simplify that fraction a little. We can make the equation look even simpler if we multiply it by 1. But instead of just multiplying it by 1 over 1, let's multiply it by this fraction. This fraction has the same thing on the top and the bottom, so it really is equal to 1. But when we multiply by it, it makes our equation look much simpler, because terms in the equation will cancel out. So since there are n particles, the average energy per particle is the equation we just got divided by n. which finally gives us our result. Now, in an earlier video, I talked about the equation they got for blackbody radiation using the physics they knew about before Planck. That was called the Rayleigh equation, and it looked like this. In this equation, what you have is the average energy per particle, which they said was k times t. The rest of the equation, this number, takes you from the average energy per particle to the overall energy. When Planck multiplied his average energy per particle by that factor, he got this equation for the overall energy. And that's our result. That's now known as the Planck equation. If you use this to plot out the energy of a blackbody, you get a graph that's just like the energy spectrum of a real blackbody, like a star. And that was the first evidence we had that thinking about energy as coming in little units called quanta can give us better results than thinking about it any other way. It was the first step in developing quantum mechanics. Now, if you're curious to know more about the Rayleigh equation I mentioned earlier, I've also made a video about that one. Also, if you haven't seen my non-mathematical video about blackbody radiation and why we care about it, I hope you'll give that one a look too. Thanks for watching.